Hello students, welcome back to another video of metric spaces. We will start the last chapter of this metric spaces series of T.Y.B.Sc. So the last chapter is connectedness. Connectedness. So first of all, we'll see the definition of separated sets. Separated sets. So generally we say that the separated sets are disjoint set, but there is a little bit difference between separated sets and disjoint set. Two sets A and B are said to be disjoint if their intersection is empty, but the separated sets A and B, two sets A and B are said to be separated if A intersection B closure is empty and A closure intersection B is also empty. So the definition of separated set is, let XD be a metric space. XD be a metric space and A, B are the subsets of that X, are the proper subsets of X. Then the sets A and B, the sets A and B are said to be separated, if A intersection B closure is equals to phi, that is A intersection B closure is empty, and not or here, and A closure intersection B is also empty. A closure intersection B is empty and A closure intersection B is empty and A intersection B closure is empty. Then A and B are said to be separated sets. So there is difference between separated and disjoint. Two sets are said to be disjoint. A and B are said to be disjoint if A intersection B is empty. But there is little bit difference between separated and disjoint. So A and B are said to be separated if A intersection B closure is empty and B intersection A closure is empty. So if we take one example of, suppose the sets A is equals to open interval 0 1 and suppose B is equals to the set open interval 1 comma 2, then if we find the A closure, then we get close interval 0 1 is closure of A and B closure is equals to close interval 1 comma 2. Now if we find A intersection B closure, then A intersection B closure is equals to A is open interval 0 1, B closure is close interval 1 comma 2. So their intersection is empty. Here 1 is not in the intersection of A and B closure. Also A closure intersection B. A closure is this close interval 0 1 and B is equals to open interval 1 2. So this B does not contain 1. Here A closure contains 1, so 1 is not in the intersection of A closure intersection B. So A closure intersection B is also empty. Therefore, the given sets A and B are separated sets. A and B are separated sets. So from this clearly we can say that. So we will take one definition of disjoint sets. Write one remark here. Disjoint sets. A and B are said to be disjoint if A intersection B is equals to empty. There is no element in common in A and B, then we say that A and B are disjoint. So from this clearly we can see that every pair of separated sets are disjoint, but every disjoint sets need not be separated. So write one note here. Every pair of separated sets is disjoint but not conversely. Not conversely. There is no need to write this remark and note, but just for your verification. Now we will take one theorem. These are the examples of separated sets. Now if we take A is equals to this interval and B is equals to suppose interval 1 by 2 to 2, then they are not separated. To check the sets are separated or not, we will just find the closure of every set and take the intersection of A closure with B and A with B closure, and both the intersections are empty, then we say that A and B are separated sets. Now we will take one theorem. Statement of the theorem is, let XD be a metric space. Let XD be a metric space and A comma B are the subsets of X. A and B are the subsets of X if distance between A and B, distance between two sets. We have seen this definition in before the topic of diameter of a set. So distance between two sets is the minimum of distance between elements of these two, that is if we find the all elements of A and B, all elements of B, then the minimum of distance between suppose X and Y, where X and Y, X is the element of A and Y is the element of B. So smallest distance between two sets is the distance between two sets. So distance of AB is greater than 0, then A and B are separated sets, So to prove this theorem, we have given that A and B are two subsets of X and distance between A and B is greater than 0, and our claim is A and B are separated sets. So let the distance between A and B is equals to suppose lambda. Suppose the distance between A and B is equals to lambda. Then by definition of distance between A and B, we can write lambda is equals to distance between A comma B. Lambda is equals to infimum of, that is infimum of, lambda is equals to infimum of smallest distance between A and B for A belongs to A and B belongs to B. Infimum of distance of AB such that A belongs to A and B belongs to B. So suppose this distance of AB is equals to lambda and that distance is greater than 0. So this distance must be greater than 0. Distance of AB means suppose this is set A, this is set B, then these are the elements of A. Suppose these are the elements of B, then if we find the distance between these 2 points and all the points, then we get, suppose this is also element of A, this is also element of B, this is also element of B, then we find the minimum of distance between AB. So this is the minimum distance. Or if we take one element which is very close to this point and this is, so this will be the minimum distance. So minimum of distance between A and B. If we find the distance between these two elements, again these two elements and these two, all the elements, then for the smallest distance between these 2 points, that is distance between, infimum of distance between A and B is the distance between two sets. So this is the definition of distance between A and B. So here clearly lambda is greater than 0 and lambda is equals to infimum of distance between A and B. A belongs to A and B belongs to B. So we can use the definition of infimum. That is, infimum means smallest among all the elements. So therefore by definition of infimum, distance of AB, infimum of distance of AB is greater than 0. So we can write distance of AB is less than or equals to 0. It's strictly less than 0, so we can write less than or equals to, greater than. This is strictly greater than 0, so we can write distance of AB is either greater than or equals to 0. So distance of infimum of distance of AB is equals to lambda. Infimum of distance between these two elements is equals to lambda. Lambda greater than 0, so we can write distance of AB minimum distance of AB is equals to lambda. So for a distance of AB or all the other elements, suppose distance of A1 and B1 is equals to lambda, then other distances are clearly greater than that lambda. So we can write distance of AB is either less than or equals to lambda, is less than or equals to lambda, since lambda is minimum among all the distances. So all other distances are greater than that lambda. So distance of AB is less than or equals to lambda. Less than or equals to means whenever the distance of AB is minimum, in that case we get distance of AB is equals to lambda, and all other cases the distance between A and B is greater than lambda, since lambda is the minimum distance. So distance of AB is greater than or equals to lambda for all A belongs to A and B belongs to B. This is the by definition of infimum. Now this A belongs to A, so then that A cannot be a limit point of B. A belongs to A, so A cannot be limit point of B, since there is some distance between A and B. So clearly, if suppose this is element A, then that this element A cannot be the limit point of B. If we draw the open sphere, then that open sphere lies inside A or light. Just if you take this radius and draw the open sphere, then this open sphere does not intersect B, so that A is not in the limit point of B. So we can write, if A belongs to A, then that A cannot be a limit point of B, since if we take the radius, suppose lambda by 2. So if we take, suppose this is the distance lambda, and if we take the radius, suppose this lambda by 2, suppose this is A, and draw the open sphere, then this open sphere lies inside. And definition of limit point says that for every radius greater than 0, that open sphere must intersect B, then we say that that element is limit point of B. So if we take lambda by 2 radius and draw the open sphere, then that open sphere does not intersect B, since yes, lambda by 2 of A does not contain any point of B, does not contain any point or any element of B. If you take this radius and draw the open sphere, and this open sphere does not contain any point of B, therefore we can write A intersection with B closure is equals to empty. A was the element of A, and for that element we can draw the open sphere. So this A is arbitrary element of A, and for that A there is some radius such that open sphere does not intersect with B. This means every element of A is not a limit point of A, that is every element of A. If you draw the open sphere around every point of A, then that open sphere does not intersect B. So every element of A is not limit point of B, implies that A intersection B closure is equals to empty. And similarly we can prove that A closure intersection with B is empty. A closure intersection with B is empty, hence A and B are separated sets. A and B are separated sets, hence the proof of given theorem. Now the next theorem is let XD be a metric space. Let XD be a metric space and A comma B are the subsets of X. B disjoint sets. Disjoint means their intersection is empty. A and B are disjoint sets. Then the first statement is, if A and B both are closed, then A and B are separated. separated sets. Similarly, the second statement is B. If A and B both are open, then A and B are again separated sets. So disjoint closed sets are separated, again disjoint open sets are separated. So we have given that XD is metric space, A and B are disjoint sets. In the first step, A and B are in the first statement. If A and B both are closed, then A and B are separated. And in the second statement, if A and B both are open, then also A and B are separated. So first of all, we have given that A and B are disjoint sets. So in the proof, we have given that A and B are disjoint, that is A intersection B is equals to phi. A intersection B is equals to empty set. So this will be useful in this whole proof. So we will denote it as by equation number star. So to prove the first statement, we have given A and B both are closed sets. So let A and B both are closed. Both are closed sets. Therefore, the A is closed and B is closed. So A is equals to A closure and B is equals to B closure by definition of closed sets. A is equals to A closure, B is equals to B closure. Since we have given that A intersection B is equals to phi, since A intersection B is equals to phi, but here A is equals to A closure and B is equals to B closure. So we can write A is equals to A closure. So A closure intersection with B is equals to phi, and putting B is equals to B closure, we can write A intersection B closure is equals to phi. Just putting A is equals to A closure in this equation, we get A closure intersection B is equals to phi, and again putting B is equals to B closure in this equation, we get A intersection B closure is equals to phi. So A intersection B closure is equals to phi and A intersection B closure is equals to phi, we get, so we can write A and B are separated sets. A and B are separated sets. Hence the proof of first part. Now to prove the second part. The second statement is A and B both are open. So we have given that let A and B both are open sets. Both are open sets. Our claim is A and B are separated sets. So claim is A and B are separated sets. A and B are separated sets. So now we will prove this result by contradiction. On contrary, we will suppose A and B are not separated. That is, A closure intersection B is non-empty. A closure intersection B is non-empty and A intersection B closure is non-empty. By contrary, I assume that A and B are not separated sets. So on contrary, we will suppose suppose A and B are not separated. A and B are not separated. That is, this implies that either A intersection B closure is non-empty, or A closure intersection B is not equals to phi. Definition of separated sets means A intersection B closure is equals to phi and A closure intersection B also equals to phi. But we are contrary supposing that A and B are not separated. Then either one of these conditions fail. That is, either this condition fail or this condition fail. This condition means A intersection B closure fails. That is, A intersection B closure is non-empty, or A closure intersection B is non-empty. Then we say that A and B are not separated. So we will suppose the first condition fails. So without loss of generality, we will suppose A intersection B closure is not equals to phi. In general case, we cannot say that either this fails or this fails, or this holds or this holds. So we can take, suppose this condition is, or that is A intersection B closure not equals to phi, that is their intersection is non-empty. So their intersection is non-empty means there exists some element, that is suppose x belongs to A, such that there is some element x belongs to A intersection B closure. X belongs to A intersection B closure means x belongs to A and x belongs to B closure. X belongs to A and x belongs to B closure. Now x belongs to A and A is open set. By supposition we have A is open set. Therefore there exists some radius greater than 0 such that SR of x must lies inside the A. Since A is open. Since is open. So by definition of open set, open sphere centered at x lies inside the A. Also x belongs to B closure. So by definition of closure, we say that x is limit point of B. A is said to, A closure is defined as set of all limit points of A. So here B closure, x belongs to B closure means x is limit point of B. Now x is limit point of B, just write. Also x belongs to B closure, that is x is limit point of B. Therefore we can write SR of x SR of x minus singleton x intersection with B is non-empty. SR of x minus singleton x intersection with B is non-empty. Say x is limit point of B means for every r greater than 0, if you take any radius, then that open sphere minus center intersection with B is non-empty. This is the definition of limit point. So for that we will take r is equal to this r. We take for any radius we have this intersection is non-empty. So we will take r, these two r's equal. Now SR of x totally lies inside A, and this SR of x intersection with B is also non-empty. So from these two we can say that this open sphere lies inside A, totally lies inside A. Also this open sphere intersect with B. So these two equations says that A intersection B is non-empty. This implies A intersection B is not equals to phi. Since suppose this is set A, now suppose this is another set, suppose B, this is A, this is B. Now if we take one element of X and also that element of B closure, so that element must be here. So A is open and B is open, then we cannot take the element on the boundary, so we have to take that element here. Now if we take this element and draw the open sphere, then that open sphere totally lies inside A, then that open sphere does not intersect B closure. Now to intersect, that means to intersect with B, that open sphere must be this. Now this open sphere, this is not possible. If we take one element for which the open sphere totally lies inside A, then that open sphere does not intersect B. Now to hold this condition, our diagram must be, suppose this is set A, this is set B, then this is the element of A for which if we draw the open sphere centered at that element, then that open sphere lies inside A as well as intersect B closure. So to hold both the condition, that is SR of x lies inside A and this SR of x intersect with B, A and B must be intersect. So this says that is this open sphere lies inside A and this SR of x intersect with B. So this implies that intersection of A and B not equals to phi, which is contradiction to our equation number star, which is contradiction to equation star. There is no need to draw these diagrams. One thing must be clear, that SR of x to be in A as well as SR of x intersect with B, this diagram we have to draw this diagram. In this diagram there is no possibility that, suppose if you draw this A, so this is B, then if we draw the open sphere which totally lies inside A, then this open square does not intersect with B closure because B closure is this set. So to hold the both the conditions, our A and B must be intersect, but which is contradiction. Now suppose this condition by contrary, so we have to get some contradiction. So this A intersection B not equals to pi. This is contradiction to equation number star. Therefore, our assumption is wrong. That is A and B are not separated. This assumption is wrong. Therefore, A and B must be separated sets. Therefore, A and B are separated sets. Hence, the proof.